So basically, in terms of this talk, it's going to be a very technical talk and related to data mining research. And this specific topic actually just published in KDD 2007. That's August. I just attended the conference. But before I go into such technical detail, I know these are ECE department, so I would like to give some brief background about data mining literature. So first, let's look at some commercial point of view, why we want to do data mining, particularly nowadays. And we can easily observe now we have a lot of data has been collected. Say, for instance, supermarket. Walmart has a lot of retail data collected. And about the web. So those kind of web documents has been accumulated a lot. And also some bank credit card and transactions. So basically, the idea is now we have lots of data has been collected. The reason is very simple. Now we have a very cheap hard disk, and also the computing power becomes very powerful. So now we come to the question, how can we make use of this data and to make money or to advance our research? So from the business perspective is try to use the data to turn this data into the money. And so far, the Google is the most successful company to turn data into money. So you guys may not be realized. Say, for instance, just give you one example. Last year, during the Thanksgiving, the Google has the campaign like Google Checkout. I'm not sure any of you guys tried that. So basically, once you try Google Checkout, they give you some discount. And but you also sacrifice something you may not realize. You just give your data, say for instance, your home address, what you purchase, which day, and how much money you spend, your credit card information. You give all this information to Google. So Google then is going to use some data mining techniques, doing some, say for instance, customer segmentation analysis. And then they are going to generate a customer report. Then this customer report is going to sell to those kind of small e-commerce website or some other company. So Google actually is the most successful company in turn data into money. So that's from the commercial point of view, why we actually want to do data mining. And now from a scientific point of view, this is more relevant to us, to the students sit here. So basically we can see nowadays we have a lot of scientific data has been collected. Say for instance, this remote sensing data and also the microarray gene expression data has been collected. And also, even I'm not so familiar with your area, but I believe there are a lot of this kind of engineering data has been collected as well, particularly for the sensor network or some other telecommunication network. Say for instance, I know AT&T has a lot of data, all kinds of data. So now we're dealing with the data in the unit like gigabytes. So traditional technique is almost impossible to do the large-scale data analysis for this kind of large-scale data. And now, what data mining can help us? So traditionally, in the biological domain or many other domains, domain experts, simply by observation, the experiment data, and come up with some hypothesis, and use this hypothesis to guide further experiments. But those things is more manually, or at most semi-automatic. But from data mining perspective is, since we have already collected so large data, and it's almost impossible for human being to manually inspect all the data and come up with the hypothesis. So in scientific domain, there's one promising direction for data mining is actually people are doing this. They use data mining so-called computational methodology to automatically generate those kind of hypotheses. And then this hypothesis can guide the expert. The expert is going to looking at this hypothesis and then doing, well, it's sort of like screen. Once you screen, and then they can look at it in detail. So this is from scientific point of view. It can help us to advance our research as well. Let's look at some motivation. And there are many things, knowledge, information, pattern, which are actually hidden in the data that is not really so obvious to us. So basically, the human expert traditionally human expert, they are going to take weeks to simply find useful information. Say, for instance, people work in FBI or CIA. They're looking at a lot of data manually. They try to come up, summarize some pattern or knowledge. But nowadays, we can do this automatically. And this curve, we have two curves here. This blue one corresponding to the number of people who actually can do data mining or can do data analysis automatically. And this line, exponential growth, corresponding to the amount of data we actually accumulate in this world. And this growth is exponentially growth. So that means there's a gap between these two. The number of people who actually can do data analysis and the amount of data we actually collected, there's a huge gap. And this gap becomes wider and wider. So that means there's a need. We need to train more people who can do data mining. So just give you some statistics about how large the data can be. This number is a little bit outdated, but still, this number actually is growing very fast. And you can see now it's terabytes. It becomes very easy. You can observe. So for instance, France Telecom, they have easily have terabytes collected every month or every year. So now our expectation is we can develop some computational methodology which can manipulate those kind of large scale of data very quickly in a very efficient manner. So this is the scale of the data issue. So what we actually expect data mining to some kind of query or answer to our problem is, say for instance, traditional database we can do query. But for data mining, what kind of new stuff we can come out? Say for instance, data mining expect to answer this kind of question. Say for instance, once you give the credit card transaction data or customer data, can we answer the question like find old case of fraud? And also, can we answer the question to the marketing people? Say for instance, how to find old individuals who would like to buy this car? So those kind of questions, intelligent question. Traditional database system cannot answer this kind of question. So we have to develop intelligent engine which can answer those kind of a little bit more higher level, more like human intelligence, these questions. Say for instance, this one would be very interesting. Say for instance, you have a case for this customer. Can you immediately issue a query, find all other case which has similar problem with this case? So this kind of query is very interesting to develop. So now let's look at a little bit the core definition for what's data mining. So the data mining basic idea is we try to use some computational methodology to extract some keywords like implicit and previous unknown and potentially useful information from the data. So these some keywords we should keep in mind. So this will be automatic or some semi-automatic ways to do this kind of computation. This diagram basically shows some basic data mining practice. Say for instance, you have the input data. This input data can be any kinds of raw data. So once you have raw data, because this raw data can have missing data, can have noise, and also you have different variables and also different characteristics. So depending on what's your objective, what kind of things you want to find, you are going to do data pre-processing first. So this data pre-processing will have many things like get rid of noise, data cleaning, and also doing some feature selection, dimension reduction, normalization, and also some various things you can clean your data and normalize data, pre-process your data. Then you have some fundamental data mining tasks. We are going to touch this next slide. And once you get in the result, basically you apply some tools, data mining tools, on this data, and then you can get in some pattern. Then once you have this pattern, you are going to do some post-processing. That means you have to understand the result. You use data mining techniques you find. So then you get the knowledge. Two concepts. One is what's not data mining. Say, for instance, you just take a phone directory, you find the phone number for a person. This kind of thing is not data mining. And what's data mining? Say, good example will be, say, for instance, you can apply some computational technology. You can find that some names are more popular in certain small area in US locations. And also, I can give you more interest. Recent story is National Geographic. They have a very interesting study. They apply some data mining technique they find. So basically, they find that on the East Coast, there are more single women. The West Coast, there are more single women. So basically, they use this kind of technique they sell this kind of report. Well, of course, they have more details than this. I just give you this some so obvious things. They sell this kind of report to many companies. So those kind of commercial companies, they develop some business promotion plan to take advantage of this kind of information. So that's another example. That's what we call data mining. So essentially, data mining is an interdisciplinary area. It's a recent area. So basically, it's most likely starting from 2000. That's we can formally call it data mining. So this area is interdisciplinary area, which basically include the knowledge from statistics, machine learning, pattern recognition, and also database technology and techniques and optimization techniques, and also the visualization. So basically, it's more like they borrow the idea from this different area and they try to work on the large scale of data. So if you have any question, can feel free to stop me. I would like to answer the question. That's no problem. So this area is relatively young, but roughly speaking, we have 4 categories of data mining tasks. The first category is clustering, we so-called. Clustering idea is fairly simple. So basically, you try to group similar things together. So basically, if, say for instance, if you see a bunch of fruit, you just group apple together, orange together, and the banana together. But one thing is clustering is unsupervised. Say for instance, you can just ask a person, assume that this person do not know this is apple. He never see apple before. So, but they can, based on the shape, color, they know they are similar. Say for instance, you give 2 apples to this guy, he can recognize they belong to the same class. So this we call the unsupervised. So basically, they do not have the label for these kind of things. Say for instance, assume that somebody never see this computer before, and you give him 2 laptops. He know both of them are similar to each other. So this we call the grouping or clustering. We just simply group similar things together. That's all. So this is one big category. The second category we call the association mining or association analysis. In statistical domain, people call it, we try to find the correlation between different events. So this we call the association. How can we find the correlation between these different events? One simple example, don't look at this diaper milk example. You can look at a more interesting example from the Amazon.com. I believe you guys have the experience in purchase some books from Amazon.com. Usually once you select a book, they are going to recommend another book to you. So those kind of technique is we call association technique. So basically, you try to identify the items or products which are frequently purchased together by the customer. So those kind of information you can capture by association analysis. The third category we call the prediction. Prediction, say for instance, SVM is one example about prediction. So prediction is more like classification. So this will be a supervised learning. I'm going to have a little bit more detail later on. This we mean by supervised because we have a collection of training data, which we have already have the class label. Say for instance, this label we have already labeled. I tell you this is apple. Say for instance, assume that you don't know before, but now I tell you this is apple. We call it as apple. Now you can identify from the testing data. You can find old apples for me. So that's what we call the prediction. The last category we call the anomaly detection. Anomaly detection is something like we try to identify the abnormal events within this red circle. So in other words, these things must be very rare. That means not so frequent compared to the majority, and which is not similar to the majority. So basically try to find outlier. So find the things which are significantly different from the majority. That's the things we are going to find. So we have 4 categories of data mining tasks. A little bit detail about the clustering, because for the talk I'm going to introduce later on, I use clustering. So it's worth introduce more time. I spend more time introduce this concept. So basically, you just find the things which are similar to each other, just like this circle. The objective is to try to group the things, similar things together, and the different things put into different group. So that's the objective for clustering. So we have 2 concepts. One is intra-class distance should be minimized, and the inter-class distance should be maximized. I have already reduced the use of mathematics in this set of slides. So basically it can help you understand this better. So clustering can do many things. Here's one example from my research publication. So basically, we can use this technique to try to identify the stock company. Say, for instance, we all know that it's almost impossible for you to predict the stock price is going to rise or going up or going down tomorrow. But one thing you can do, and actually we have already shown it, you can identify a set of companies, their stock price going up together or going down together. So basically they have some similar pattern. So maybe have some time lag. Say for instance, stock A going up, maybe after half an hour, stock B is going up as well. So this kind of pattern we can identify. And also, the clustering technique can help you to do the summarization of the topic. Say for instance, if you have way too many data variables or data points, you try to understand the global picture. You can use the clustering. Say for instance, this can use the clustering, you can see the effect of the climate from a global scope. So this is doing summarization. This is another use of this technique. In terms of clustering techniques, my research focus is I'm trying to understand the strengths and the weakness of clustering algorithm as well as the clustering validation measure. So because my work along this line is relatively mathematical oriented, and it's not good to use. Even I have recent papers on this line. So basically, but it's so mathematical oriented, I'm not going to use this one to introduce for this talk. But this is my research objective for the clustering research. And for the association analysis, as I illustrate, it's quite simple. You just try to identify high correlation stuff. Say, for instance, try to identify a group of objects which are strongly correlated with each other. For your case, maybe you have the network data. You have different network events. So you may be interested in identify those kind of network events which are strongly correlated with each other. It can help you to understand many things in your research. Actually, this topic, I actually spend a lot of on this topic. That's my dissertation topic. So I actually have quite a lot of work along this line. I published the IEEE transaction and many conference, and also my focus is trying to develop an analytical model foundations for this we so-called correlation computation. This will be more algorithm oriented, but this is not the focus of this talk. And here's another interesting example. So basically, this is more sort of like my work. This is also my work, extended along spatial domain. We try to identify the spatial events which are frequently collocated together. You can find many this kind of stuff in the real world. Say, for instance, you can notice that, say, for instance, the McDonald's and Burger King. Those kind of things, they are usually their store is very nearby and located together. And some other many stores, they have a co-located effect. So basically, this is trying to identify the special events which are frequently co-located together. This is also belongs to the category of correlation computing. The next big category we call the predictive modeling. It's also called classification. This work, I mean, the COG, local decomposition for real class, is fitting this category. So basically, we have training data. Say, for instance, we have, this is just some toy example. So we call this as the training data. We have training data, say, for instance, this customer. We have a bunch of information about this customer. And then we have the class based on previous experience. Say, for instance, we know this customer is valuable. He always pays his credit card on time. And this is a valuable customer. And also, we may identify some customer based on his history transactions. We notice that this customer, say, for instance, he never pay, or he always late to pay his money. So in this case, we just label by human. These are not so creditworthy. So once we have this labeled data, we call this as the training data. Based on this training data, we are going to build a computational model. So this computational model, we call it as a learning model. So it's no longer human being, but a program, a machine. It's going to develop a learning model built on top of this training data. Then we are going to apply this learning model to predict the future events. I'm not sure you noticed that nowadays you can apply your credit card online. Say, for instance, you go to a credit card company, input your information, and maybe you wait for 2 minutes, 1 minute. They can tell you whether your application is approved or not. There's no human being sit behind, just this program. So basically, this program, based on the input information from you, they make a judgment. See whether approve or not approve, that's all. So this we call the prediction. So this is another application of data mining techniques. Now credit card company use a lot for this kind of technique. So this is the example. Say, for instance, you have the training set, build the learning model, and this learning model apply this test data set, and then you give the label for this one.
So is this really data mining? It seems like it's just sort of going through a flowchart, like making binary decisions at each stage. By data mining, you meant a huge body of data, and you go through, you dig through the data, and you find some pattern, going by your previous example.
Yes. Actually, in terms of classification techniques, you have all kinds of. You just mentioned that's a decision tree. That's one type. And also you can have a Bayesian network. And also you can have support vector machine. And also you can have a neural network. And you can have LDA, linear discriminant analysis. So basically, these different classification techniques, their purpose is they try to learn things from the things they have already know. Say, for instance, we already have the label. Once we build this learning model, this knowledge, then we can use this knowledge to guide, to learn the things we don't know. So that's the basic idea. But particularly now, this, as you just mentioned, now this training data will get large. So the learning process can be complex. And actually, this is, we are going to know this. That's actually the focus for this talk. So here's the one application. Say, for instance, you can predict the fraud detection in credit card transaction, as I just mentioned. So the last category for the data mining task is we can try to find anomaly detection. So basically, this we call this is unsupervised, and anomaly detection is try to identify some abnormal events from the normal events, but these events must be not so frequent. Outlier, we try to identify them. So this is the last category. This is I believe it's a very interesting slide. I summarize these slides based on my experience with data mining for so many years. So data mining has the most similarity to medical doctor, basically I mean. So you can see that data miner are dealing with the data with different data characteristics, but the doctors are dealing with the patient with different symptoms. So, and also data mining has a bunch of data mining techniques, which more like a medical device, which you can use to help you to understand the data and also help you to understand your problem. For the doctor, they have the medical device to understand your symptoms. So these two has the most similarity. But from here, we can inference something beyond this. You just say for instance, doctor, what kind of doctor is more valuable? So basically, the doctor has more experience. They understand the strength and the weakness of all kinds of medical device. And they can link certain disease with a set of symptoms. Say, for instance, they can observe this set of symptoms. Then immediately, this experienced doctor can link to certain disease. The same thing happens for data mining. So a good data mining person, they must be very familiar with the weakness and the strengths of all kinds of data mining techniques. And also, they understand the different characteristics of your data. So once they observe certain data characteristics, they can immediately identify the right tools to apply on this problem. Just to give you one example, say for instance, I used to attend a conference, and some people, they publish a clustering algorithm. They just say that based on this validation measure, and my clustering algorithm is the best. So, but if you're looking at a little bit of detail in his paper, you notice that he used the data really has a problem. Say for instance, the validation measure itself has a problem. This validation measure is not good fit for that kind of data distribution. He actually used those kind of data. So basically, he used some misleading technique as the guide for his own tools. So it's just like a doctor. You use the wrong tool, wrong medicine to help for your patient. That's going to cause big trouble, big problem, because you don't even understand what this tool can do. You apply this tool. So that's why I feel the most similarity between these two. That's very interesting to notice. So basically, for data mining people, it's more like a doctor. Once you have many years experience dealing with all kinds of data, then you can do a good data analysis. This has to link to your many years experience. So some students just graduate, they simply come to me just say that I can do data mining. So basically I ask him some question. So what if I give you data, how can you do data mining? He just said that I have the tool available, I just run the result, get the result, that's all. So that's not the right way to think about data mining. You first need to look at your data, understand the characteristic of your data. It's just like you have to understand the symptoms of your patient. Then you can pick the right tool, and also you have to understand problem. So this some similarity. Now that's enough for the basic background. I'm going into the technical detail of this work. So basically this work is local decomposition for real class analysis. And before I start, any question for the things I just introduced? Okay, any question you can ask? So, is there any question?
Is there really any difference between the clustering techniques and outlier detection? Are they kind of the same thing?
They have the similarity between these two. So it's quite open. Say for instance, some people develop this clustering technique which can help for identified outliers. So they have the similarity, but the objective is slightly different. So basically, the purpose for outlier detection is we try to identify a small collection of objects which are outliers. But for the clustering, is we have to dealing with the whole objects. So basically, we have to know the global distribution of these objects. The purpose is different. The clustering is more dealing with the old objects. For outlier, we are focused on some outlier. For the rest, the majority, if they are similar, we don't care. So, but in terms of techniques, you can apply clustering technique to find outlier. That you can do. Did I answer your question? And any other question?
I know it's just an example.
Yes, that's just a simple example.
But it will actually deny credit to a graduate student who is less than 3 years, even though he's completed 7 years of high school and undergrad.
Okay. Yeah, I didn't notice that. But this is just a toy example.
Yeah.
I understand. So, if no more question, I can start my work on specific this topic. So, before I start, I just want to highlight the difference between real class analysis and outlier detection. Both purpose is try to identify the minority, infrequent things. But the difference between these two is real class analysis is more like classification, it's supervised. So basically, we know the label for certain observations. Say, for instance, network intrusion detection. We already have the expert to label certain intrusion. So we see this pattern. We see this observation. We know this is intrusion to our network. It's an attack. So these are labeled. So that's we call this as real class analysis. But for outlier detection is, we don't know it's attack or not, but we know this thing is different from the majority. Maybe attack, maybe not. So those kind of things is not labeled. We call it as unsupervised. We don't know it's what kind of category they are falling in, but it's unsupervised things. So here's the outline. I'm first going to give some background introduction. And we can see real class, of course, as I just mentioned, we have many applications. Most relevant to you guys may be network intrusion detection. That will be very relevant to the WINLAB work. And also, there are many diagnoses, some real events or some failures in the system. Failure events is not going to happen very often, but it do happen. So this kind of things relatively rare compared to the majority. So this can categorize into the real class analysis.
Does rare class analysis correspond to the outlier example?
Yes, as I just mentioned, real
by rare class you mean something which is does not belong to the bulk of
the real class analysis. We mean that those kind of events are rare. That means infrequent. Outlier, which are also correspond to the events which are infrequent. But difference between these two is real class analysis, we already have the label for some previous observation. So that means we already have the knowledge. See, this observation with this certain kind of characteristics which will be corresponding to an attack. So this attack is the label we put associated with this observation.
So this classification, is it sort of a deterministic model, or it's more like a probabilistic that you would go wrong sometimes and you might, like there's a probability or miss or a probability of...
You can put it this way. Classification model, some people can use a probability model to build a classification model. Say for instance, Bayesian. Say for instance, you can see that if the probability above a threshold, say 0.8, you say this belongs to class A. If less, belongs to class B, otherwise. So this probability model, you can build a classification model. And also deterministic model, and also you can also, say for instance, decision tree. You can just say, you have these certain attributes, so these certain values, you are falling in this category. So this is determined. So both can be used for the classification. One very important difference between these two is classification is a supervised learning. We mean supervised is we already have the training data. Those kind of observations within the training data already have the label. It just say you put some fluid in this training set category. You tell the people, we label this one as apple, this one as orange, this one as banana. But somehow, in the testing case, you have a bunch of fluid put in there, and you don't know the label for this one. So basically, you can, based on the training, you have already know the label, build a learning model, then predict the label for the new one. So this we call the supervised. And the unsupervised, so basically we mean we have no label for any objects, for any observations. But based on the similarity, we simply group them together. Say, assume somebody from really outside, not human being, and they don't even know what's this. But you put several laptops together, they know they belong to the same category. They know they look similar. So this we call the unsupervised. We do not have a pre-knowledge about the label for this observation.
So in terms of technical challenges, the real class analysis has fewer technical challenges than the outlier detection, since it has already prior knowledge.
Supervised.
This real class is falling into the category for the classification analysis. It's supervised. Outlier detection is unsupervised. If these are supervised, so we can adapt the supervised techniques to help this problem. Traditionally, both supervised and unsupervised, we can call it as learning problem. Both are learning problem. It's just like we have a big hierarchy. We have learning problem, then we have a supervised learning problem, we have unsupervised learning problem. Usually the supervised learning problem can have a better performance compared to the unsupervised because you already have the knowledge, pre-knowledge about certain observations. So that's the difference. So these are supervised. First, they fall into the category for the classification. And this we do the real class analysis. We mean real class, so basically just like give you example you can quickly understand. Say for instance, the patient has certain cancer disease. Those patients with this cancer compared to the large population is very rare, infrequent, right? You go to hospital, not many people has cancer, right? Only very few. So that means not a large population, very small population has this kind of label. The large population has different label. And also it's just like network intrusion. Not every network access is an attack. Majority are not. Majority are just normal access. You can label them as normal. But some, you not label them as attack. You already know that's attack, right? So this problem setting just like that. In terms of research motivation, real class analysis is one of the most challenging problems in the classification. Because we are dealing with an imbalanced class distribution problem. So as I just mentioned, you have normal network access. You have very few attack. So this kind of learning problem is the most challenging learning problem in the supervised learning. And this is an unsolved problem. So far, there's no technique that can handle this well. So
What's the answer?
there's no solution.
What is the problem exactly?
The problem is, say, for instance, you try to predict those kind of real class.
Supervised.
Yes.
So you have some training data, and for a given instance, you need to determine whether it belongs to class A or class B.
Yes, let me use the network example. Say, for instance, now you try to predict the network intrusion. So you already have some observations. Say you have the observation, and some expert has already labeled this kind of observation. Say, for instance, they somehow label 1% access, which are attack. 99% are normal access. So you already have this data. We call the training data. Now you are going to, based on this training data, build a learning model. Now you can use this learning model for future online access. Now you have new access. Now you have to label them. Is attack, not attack, attack, not attack, something like that. So that's the problem.
This is an open problem.
Yeah, this is an open problem. You can abstract this problem. This will be a specific problem setting in network area. But this problem you can abstract becomes a common problem for many domains. Say, for instance, patient. Now, medical domain, you can develop this kind of diagonal system, and which you can label this patient has cancer or not.
But I guess you can assign probabilities to each of the classes, right? Based on the instance of the observation. You can say with probability so and so it belongs to class A and probability so and so.
Yeah, as I mentioned to you before, for this kind of supervised learning, you can have different approach to deal with this problem. Probabilities model is one way. You can assign the probability for every observation, say how much percentage you are the attack. But quite often people put a cut line. Say for instance, if the probability greater than 50%, you say it's attack, otherwise not. So the probability is just one way, it's a Bayesian. We are going to have that. So our research motivation is the current existing supervised learning techniques. They cannot dealing with this kind of linear. They can only deal this kind of concept very well. Say for instance, linear separable. If we have two classes, one class is here, one class here. For the linear classifier like SVM, they can identify these two classes very well. Even these are real class, small set, because they can easily make a hyperplane to make a cut. But for this case, will be difficult because it's very difficult for you to draw a linear line. And this case will be even more complex. The three classes mixed together, so you cannot find a hyperplane which are linear separable to separate these three classes. So this is the research challenge. So the problem setting, as I just mentioned, we are trying to develop algorithm to predict those kind of, say for instance, the network intrusion, those kind of real class. That's our major objective. So the hypothesis is we are going to dealing with the data set with those kind of complex concepts as illustrated this. But we are going to make use of the clustering technique. The clustering technique to help us for this purpose. So this contribution, let me skip this one. So now let's look at how exactly we can do that. So here's the objectives of our method. How can we actually develop a classification methodology? So which can have the ability to dealing with this imbalanced class into relative uniform class size. So that's one factor we know is if for the supervised learning prediction classification, if the class distribution are almost uniform, not this kind of skewed, say it's not like a cancer, non-cancer, it's more like a uniform distribution. Every class has almost equal size. Then the current existing learning method can work very well, like SVM, decision tree, they can work well, no problem with that. They only have trouble with this kind of imbalanced situation.
You mean imbalanced or separable?
In terms of size.
In size.
Yes. Well, of course, for this case, even imbalanced, it still can work. But most cases will be not so ideal case like this. Most cases are this case.
Why is it easier when the sizes are similar?
This one is easy one because there itself is linear separable.
No, I'm talking linearly separable, I understand. But if the sizes are similar, you said it's easier to classify than when the sizes are very different.
Yes.
Why is that?
The reason is because that means you have more information regarding the real class. It's not going to be dominated by the observations of large population. Say for instance, if your size is one is dominated the other one, then the knowledge you summarize most likely is going to be from this large population. You are not going to have enough to cover the small class. Because the learning model is going to learn from the old data. And it's just like you can think this with like a democracy, this system, voting system. Your group are simply too small. Your voice cannot be held by anyone. It's simply overwhelmed by the large population. But if two parties has almost equal size, then that can make sure the voice from either one can be held by the upper layer.
So it's about sampling issue.
No, it's not sampling issue. It's about it's more like a majority dominant effect. It's just like an election. Say for instance, if you have 1 billion people.
So I think the issue is how do you measure the sort of the efficiency of classification? Is there some metric?
Yes, you have the validation measure. We are going to introduce later. For this issue, you can think about it's more like a size effect. Say, for instance, you assume that one country has 1 billion people. Even you have a large group, like 10 million, big group, they have completely different voice than the majority. But their voice is not going to be held by anyone. I mean, no one is going to pay attention for their voice because the majority has different voice than you. So,
from a classification point of view, it seems that it's much easier when one group is huge, because you can randomly just assign it to the bigger group, and you'll be right most of the time. Right? So I guess your validation measure has some different.
The validation measure is we value the opinion of real class.
Okay.
It's just like give you example for the patient and cancer, non-cancer, right? Say for instance, if you have 1% of people, actually not so large population, 1% of people have cancer, and 99% have non-cancer. If you use prediction accuracy as the measure, that's going to be very worse, right? The easy way for you to predict every case to be non-cancer, you have 99% accuracy.
Right.
But this is not what we want for the real class. Real class, we want to get high prediction accuracy for the small group. That's the difference. So the cost model is different. We are more value those kind of real class. Say for instance, network intrusion. We are not so interested about the normal access. We are interested in those kind of attack. So that's why we pay more attention on the real class. So now let's look at the problem. So basically, how can we actually develop a classification method which has the capability in handling this kind of imbalanced class distribution, and also can decompose this complex concept we just illustrated into a simple concept. Say for instance, here I'll give you one example. We use different symbol indicate we have two classes here. One class is with the circle indicated. The other one is a little bit large size with the plus symbol. And if we use a traditional clustering algorithm, it's going to be in these two classes. So that means this class is going to be mingled together two objects from two different classes. So this kind of clustering is not going to help you to understand this complex concept. So instead, this is the approach we are using. So since our hypothesis is this way, since we know that the learning algorithm can handle those kind of class with almost uniform size, they can handle that very well. So we are going to do the clustering first in a big cluster. Say for instance, this cluster plus. We're doing clustering first within this big cluster. So in reality, we have two class labels, plus and the circle. Now, once we're doing cluster within a large class, then we have three groups. Now we make a pseudo label. So this will be, say for instance, this will be class A. Say, assume that we have two classes, plus and the circle. Now this class will be plus A, this class will be plus B, and this class will be circle. So from two classes, now we have three classes. And these two classes will be pseudo class. It actually belongs to the same class. We just make a pseudo label to make them like two additional subclass. So now we have three classes. So we turn two class prediction problem into three class prediction problem. So will be class plus A, plus B, and the circle. Now the size, you can look at their size, is almost balanced. Now we apply the traditional learning algorithm. Once we apply traditional learning algorithm, build the learning model, and then use that model to prediction the future events. And then future events is going to be mapped back. Say for instance, one event is predicted as plus A. We know it belongs to class plus. And the plus B is also belongs to class plus. So that's basic idea. So actually I get rid of all the mathematical things. So that's will be very easy to understand. So these algorithm descriptions and I'm going to illustrate use the example. From this example, you can understand the algorithm is actually fairly simple. Say, for instance, now we try to doing prediction for these three classes. This one, plus, and the triangle. Circle, plus, and the triangle. We have three classes. And we know this plus class is a little bit small compared to the other two. We cannot find the linear classifier for this purpose to predict this one. So what we can do is we're doing clustering first. We're doing clustering within two large classes. We're doing clustering use size 2. In this one, get 2 classes. And also we're doing clustering within this big one, getting 2 classes. Now, from 3 classes, we have 5 classes. And these 2 are actually pseudo class, not real class. So basically, this will be pseudo class, circle A, circle B, and this will be real one plus, and this is triangle A, triangle B. So now the 3 class prediction problem become 5 class prediction problem. And you can see the size. Their size is almost similar to each other. Now we can apply those kind of linear classifier like SVM. Now SVM is very easy to divide these 5 classes because they are very easy to find the hyperspace, hyperplane to partition these 2. And also partition these 2, partition these 2, partition these 2, partition these 2. Now if we apply SVM, we can easily get these 5 class. And once we get this 5 class prediction, we can map back, then we can get 3 class.
Looks almost like a bird diagram.
So this is it's a cute idea. Use pseudo class and try to, so basically we try to use a pseudo class to cheat those learning model and help those learning model to identify this complex structure. So this is the basic algorithm. If you understand this example, pretty much that's the key for this algorithm. The key is if you directly draw a line for this complex concept, you cannot do that. But our algorithm only has the capability to draw a line. Let's make it the extremely simple way, oversimplified to describe this. So then you introduce a pseudo class. Now allow you can draw a line to separate them. And this pseudo class, you know they actually belongs to the same class. Once go to the result, you just bring them back, then you are done. So that's the algorithm.
How does the algorithm decide how many pieces to make?
Usually, you know the size for the small one.
Okay.
So basically, roughly,
Size is one.
yeah. So this just further illustrate. It doesn't matter as long as you understand that one. Now we look at briefly about the experiment result. I don't want to take too much time. And so the validation measure, we are not going to use accuracy. First, to get to your question. We are going to use the F measure. So we are going to try the experiment on many real-world data set. That's what we are going to try, right? And the validation measure we are going to use is we call the F measure. So F measure can be used to measure the performance for the real class. So basically, target on real class. Once we target on this real class, we use this CV, that's a statistical measure, to indicate how skewed the data is. So basically, we use CV to indicate the skewness of the data. So, yes.
The traditional clustering that you showed a few slides back on the left-hand side, that just uses CV as a measure for clustering, right?
No. Clustering, we just use k-mean. K-mean is a standard clustering algorithm.
Is it just based on the distances?
Yeah, but based on the distance.
From the centroid or something?
Yeah, from centroid. That's a distance-based clustering algorithm. So we actually use the F measure to validate this result. I guess this result is, I'm going to not take too much time to show the result, but basic idea is we compare our approach, the COG with the traditional SVM. So basically, we show the result, the performance, and also we compared. These are two-class model, and we compare with SVM at different skewness, and you can see the effect. And also, we also compare with the multi-class. The above one we show the two-class prediction problem. This multi-class, class A, B, C, D, E. All these experiments using real-world data set. And also we compare with some other existing approach. So existing approach, people try to make the class distribution more balanced. They're doing some, say for instance, sampling technique. Say for instance, this class too small, this class too large. They're doing some undersampling on large class. And also they can do some oversampling on the small class. Try to make them size more balanced. And also we use some real-world experiment to compare. There's one thing you should understand. F measure is between 0 and 1. The higher, the better. If algorithm need to have F measure value, which indicate a better result.
You haven't defined F measure yet.
F measure is so basically it's just 2 times precision times recall divided precision plus recall.
What's the last thing?
The precision and the recall.
What's the recall?
Recall, so you have to get a confusion table. So basically, if you put a 2 by 2 matrix, 2 by 2 matrix, say for instance, these are prediction value and these are real value. So this will be prediction correct and which is actually correct.
Oh.
So that's confusion table. So those kind of things, and then you can get a precision recall. You can do a Google F measure, not difficult to understand. That's a standard measure, used quite a lot in the field. So you can see this. We can use this our approach to compare with the standard approach like SVM, Ripple, PNU. Those kind exist in the best approach, and we can see that for this actually we use the real network intrusion data KDD cup 99, which is a computation data. So in terms of this real class, F measure for SVM, Ripple, and the PNU actually is really bad. 2.26 is really bad result for this real-world data set because F measure is so low. But for our case, we can increase compared to PNU almost double the result. It's have already double the result performance. So this result is the most appealing result because everyone knows this KDD cup is the most tough data set. That's a benchmark for the computation in data mining area. And this result, as we can see, we compare with different approach. Say for instance, SVM is one approach, and these are Bayesian approach, prediction, and this is decision tree, say for 5, and these are Ripple's rule-based approach. And we can see the COG is work well for the linear classifier, so basically can improve the result a lot. So this result actually is to highlight compared to our approach. Say this is a clustering approach, these are random partition, and these are pure SVM. Pure SVM, that means we don't do anything else, just use SVM. So for this approach, you can see our F measure prediction can be much better for the real class. So there are some related work for the real class. The one thing is for the cost-sensitive learning model. As I mentioned, they pay more attention on the small class. So basically give more weight. Say for instance, predict if one is correct, you give 10,000 credit for one correct prediction. And for a normal one, you only give 10 or even 1. So in this way, we have some cost-sensitive model. And other ways I mentioned is you can use sampling and oversampling, resampling. Try to make the size more balanced. And the other method is rule-based method to handle in this case. So I actually don't want to go too much technical detail. So basically, some take-home message I want to make here is the first, real class prediction problem is a challenge. It's because of the size effect. It's imbalanced size. And the existing techniques is not so good for those kind of problem. So we try to use the local clustering to doing some local decomposition of large class, and try to make some pseudo class, make them size more uniform. And then we can apply this technique to improve the existing technique. So I guess that's all. I don't want to. This I joined work with my external student at Tsinghua University. And no more.
Any more questions?
Any more questions?
So